Okay, today talk for a few minutes about processors and upgrading memory. Talked about motherboards, and you're familiar with motherboards. And these are two of the primary things that go on to motherboards. The motherboard processor have to match, and the motherboard memory have to match, because you can't just go out and buy DDR3 memory and put it into an older system. An older system would use a thing called a SIM, which is a whole different shape. All these older motherboards over here actually have the SIM, which is a single inline memory module, and we use a DIMM, which is a dual inline memory module, so we kind of double that. The objectives are learn about the characteristics and purposes of the Intel AMD processors used for personal computers, and I think that you'll probably find when you do the A+ test that they focus on the Intel stuff. I'll see if I can double check with some of the other people that have taken it, but I think they probably focus on when they ask specifics on Intel. Learn to install and upgrade a processor. Install is not such a big deal. Upgrading can be a big deal because you've got to go back to the specifics of the motherboard and find out which processors it'll actually support in order to do that. And you talked about your gaming machine, you've upgraded it. You hadn't fooled with changing the processor because you probably were using the processor that you got with it. Yeah. But you change memory, video, stuff like that, things to make the gaming portion better. The different kinds of physical memory and how they work. In today's world, DDR3 and DDR4 are supposed to be on the way. We'll look at a little bit about how these things are labeled and the speeds. When we talked about motherboards, we talked about bus speed as well as processor speed. Processor speed is the thing that if you go to the Best Buy ad or the H.H. Gregg or whatever else, one of the big things you're going to see is what the processor speed is, and that's just one component of it. The other one, we talk about 32-bit, 64-bit, how much information can go to the processor at any given time. When we go from 32 to 64-bit, we've actually doubled the data rate that we're using to get to the processor itself. Learn how to upgrade memory, not such a big deal. We just kind of snap it in and snap it out. The people that sell memory locally, I think they charge like $50 to install memory, I think, over some of these places. You should check around. It's kind of amazing when you see what stores, commercial stores, charge to do things that you already know how to do. So this one, types and characteristics of processors on this one. Processors installed on the motherboard, we know that. And this is a good picture in that it shows the size of the processors combined as compared to the huge cooler fan. Cooler seems to be the popular term for the fan that goes on top of this thing, because we have this not real big piece of silicon with this huge fan and heat sink on top of it to carry the heat away. And heat dissipation is one of the major issues with computing. And when you get into data centers where they have lots and lots and thousands, tens of thousands of servers, the ability to carry that heat away becomes a much bigger issue. And our individual machine is not such a big deal unless the air conditioning goes out and it's 105 degrees. Well, with those, determines the system computing power. How fast can it process information? It doesn't necessarily, or it doesn't actually determine the overall speed of the machine itself, but the computing power, the ability to process the ones and the zeros. Two major manufacturers we know, Intel and AMD. There used to be more, and they just kind of gradually go away. And those two are the ones that we do that affect the processor's performance, the clock speed that the processor supports. And it's going to have a multiplier that goes along with it. So the speed that it supports, the processor speed, the socket and chipset the processor can use, and this goes back to what's on the motherboard. The chipset, the set of chips that supports the functionality of the computer and of the processor. The architecture, 32, 64-bit. Multi-processing, dual processors, multi-core, multi-threading, those things. Dual processors, more than one machine. The server sitting over here against the wall, if you look at it, it actually has two processors in it. So it has two processor slots. It has the ability to to run the two at a time. And when you do a dual processor or even multi-cores, you have the ability to assign a process to a processor. It's called affinity. So that if you want something to always run on a particular processor, you can set the affinity for that thing. Multi-threading allows us basically multiple connections, the ability to do to set up two or more connections to the machine. Effective processor performance, memory cache. Memory keeps coming back, and memory is a really, really, really big deal. And a cache is something that's stored for reuse. We talk about caching stuff in a browser. We cache addresses, for instance, so that when you start typing the address, it completes it for you whether you want it to or not. That's cached. In memory, it caches things that are going to be available for reuse. And we're going to have possibly 3 different types of cache, L1, L2, L3. Really, really brilliant, right? And what the numbers represent basically is whether it's on the processor die, whether it's in the processor package, or whether it's out of the processor package. And that's going to affect how fast things can operate. When we get into these things, we talk about distance and speed. In general, we think about wide area networks and local area networks. Wide area network, cable modems like, 30 or 40 megabits per second. I know you can buy higher ones. Inside the local area network, 100 megabits per second, a gigabit per second. When you get inside the computer itself, the distances become much shorter, and the speeds become much faster. So in this memory cache, the closer it is to the processor, the faster the processor can actually use the information. One of the other reasons we have this is programmers program in a logical manner so that the machine actually guesses at the instruction that's going to be needed next and reads that into memory cache, and then the processor has it at the much higher speed memory than in the dynamic RAM that we use when we talk about how big a RAM. We've got 94 gigabytes of RAM, 180 gigabytes of RAM, 8 gig, 6 gig, 4 gig. That memory is going to be slower than the cache. Support for virtualization, nice word. The only thing virtualization means is that we can have multiple instances of an operating system running on the same piece of hardware, and it shares the hardware with all those different ones. And it's a way to leverage the processing and the memory capabilities of a machine, because when you look at your particular gaming machine, if you're not playing a high intense game, have you ever looked at what your CPU utilization is? Probably somewhere around 0 or 1%. So we could run multiple machines that use like 0 or 1% at any one time. Typically, when a machine uses a lot of processor power is when you start a program up. Unless you do a video now, the video really will maintain a relatively high utilization over a period of time, but allows us to do that thing. We've got a server back here that we'll do some stuff on a little bit later. We'll configure RAID next time when we talk about hard drives. That has 96 gig of RAM, I think, and we've had over 100 computers running on it at any given time. The machines in the library, all of those are virtual machines that run on a server in the NOC. They actually, even though they appear to be Windows 7 machines, the hardware that they're running on doesn't support Windows 7. So what we actually have is a Linux installation on the hardware, a very small Linux installation on the hardware, and it does a remote desktop to the virtual machine that's running in the NOC. Works pretty well. Whether it has integrated graphics, and that's something that you gamers don't really want, is integrated graphics because it's way too slow. But when we talk about the things that we're here to learn how to manage, which is in the corporate environment, integrated graphics is probably going to be the way you're going to go. Most of the machines in this room, if you look at them, We don't really have a graphics card, well, no, not about everything. I think everything on these machines is on the motherboard itself. It's integrated into the motherboard. If the integrated graphics fails, you can disable and put as long as you have an expansion slot and put a graphics card into it. Processor, the basic components are the input-output unit, the control unit, and one or more arithmetic logic units. The ALUs, you're probably going to have at least 2 on all of the modern processors. So the input-output manages the instructions that are leaving the processor. When you notice, and we have a swap file, page file, swap file in Linux, page file in Windows, same thing, that information that can no longer be held in RAM gets put into the page file. And when it needs the processor needs that information, it gets paged back up into memory, and the oldest information gets paged from memory to the hard drive. Input-output, control unit manages the activities inside the processor, what's going to go in with it. And the arithmetic logic units perform all the logical comparisons, the calculations. What computers do really well are arithmetic. They do rapid, repetitive actions extremely well. Basic components are the registers of the small holding areas, all the counters, the data instructions. Then we talked about the caches, holds the data and the instructions to be processed in the buses. So we have registers, buffers, small holding areas where on the processor chip. And again, the closer we get to the CPU, the faster all of these things are going to be. And the speeds are going to be faster inside. And once you get on the bus, things are going to slow down. Inside the processor, we're going to run 3.2 gig maybe, and the bus may be 800 meg, so it would have a multiplier of 4, so that the processor runs 4 times faster than the bus. And the bus is 800 megahertz is going to be how fast that it would be able to send things to and from memory. And memory is where the information is held, paged in and out. Sent to, okay, we go from hard drive to RAM, RAM to cache, cache to CPU. An image here of what goes on, the things that we talked about, hopefully talked about, we'll see if this thing works, the I/O unit, the control unit, and in this one we have the 2 arithmetic logic units. The internal memory cache, and this would be the L1 cache, would be in this thing. It's an internal data bus, 32 bits wide, and when we take 2 of these things, the 2 times the 32 gives us the 64-bit architecture when we look at these things. The front side bus down here is 64-bit. So the I/O, the 64-bit goes to the I/O unit. The I/O unit connects to the control unit. The I/O unit allows things in and out of the processor component here. The control unit controls what goes on inside. The internal, because the control unit, we go into internal cache goes to the arithmetic logic units. And then we have registers up here that allow short-term storage for what goes on in the system. And registers, you see called registers or buffers when we do these things. The frequency, the speed of the processor works, and everything works at a speed of some sort. What this means, and when we talk about, and I think we did this in the, we talked about in the motherboard, I like to use 1 gigahertz because I can do the arithmetic with 1 gigahertz. A 1 gig processor is not very fast anymore, true? But at one time it was. Actually, at one time 33 megahertz used to be fast, but a gigahertz, what does a gigahertz mean in time? It means that the computer is doing something every billionth of a second. So it tries to do something every billionth of a second. Not everything can be processed at that. If the processor is running at 3.2 gigahertz and the bus is running at 800 megahertz, 800, and then we have our 3.2 gig, that's a factor of 4, right, to get there. Means that the processor is running faster than the memory. So it may have to wait for things to catch up. So the processor frequency, the speed the processor operates internally, not necessarily how fast the computer works. That's the processor. The memory and all the other supporting elements are going to affect that. That's why on your gaming machine you go out and buy a high-powered video card, because it does its own internal processing, right? And it also is going to be able to take load off of the CPU. We talked about the multiplier. The system bus frequency times the multiplier equals the processor frequency. Up here we had 800 megahertz bus and a 3.2 gigahertz CPU. So the multiplying factor would be 4. When we overclock a system, we change this multiplier factor and run the CPU at a higher speed. When you do that, you're going to produce, here we go with that magic word again, more heat. So you need to be able to dissipate that heat. You can actually cause the processor, and sometimes people overclock, the processor becomes unstable typically because it gets too hot when we want to do those things. Today, processors are sold to contain the arithmetic logic units and registers that can process 32 or 64-bit. And what we really want in most things today, I think probably just, well, most things, I won't say about everything, most things are going to come with 64-bit. The Windows program 7, 8, Vista, if you're brave enough to use it, all came with the ability to run on the 32 or the 64-bit system. Most of the systems today are going to be hybrid systems, which allow you to install either a 32-bit or a 64-bit operating system. But to take advantage of the 64 data bits, and the 64 data bits, if we go back to, see if I can make this thing go back here, the 64 data bits are the ones coming off the bus going into the I/O unit to the control unit, and it breaks them down into the two 32-bit systems. To take advantage of that, we have to have the hardware that supports the 64-bit as well as the operating system that supports the 64-bit and a 64-bit program. 32-bit processors, x86, you ever wonder why they call it x86 instead of 32 or something like that? Intel numbered all of the processors with an 86. So the 32-bit systems are x86 systems. The hybrid x86 and 64, which means that you can install a 32 or a 64-bit operating system on them. AMD produced one that was the AMD 64, and then the 64-bit processors, the x64 require 64-bit operating system. So you can buy hybrid, which do both, 32-bit and 64-bit, or a straight-up 64-bit processor, which requires a 64-bit operating system. Not that big a deal. And as we move on into the Microsoft world, when we get into servers in particular, the new servers only come in 64-bit editions. So they have kind of gone away from the, yes, everything's got to be backward compatible. It really doesn't anymore. Mentioned the memory cache, the L1, L2, L3 cache. Each core in the processor has each core in a multi-core has its own L1 and L2 cache, and they share the L3 cache within the processor package. It improves performance because this memory is much faster than what's on the bus. So it's going to faster memory. We go from RAM to L1, L2, and then it goes from there to the, we'll say to the ALU, to the processor through the control units. This system has been set up for years. It used to, I think, become more significant in the older systems because the memory was an awful lot slower than it is today. So the cache memory, which is SRAM, static RAM, as differentiated from DRAM. I'm mixing apples and oranges and getting ahead of myself, but that's okay. DRAM has to be refreshed like every clock cycle. SRAM doesn't have to be refreshed. As long as there's power on the system, it's okay. DRAM, the memory that we go out, the 96 gig that we have or whatever else, has to be refreshed on a regular basis. So we go from DRAM to SRAM, and the SRAM is going to be much faster than the DRAM. Nice picture here. Memory control unit, core 1 contains L1 cache, core 2, L1 cache, core 3, L1 cache. So each of them has their own L1 and L2 cache, and then the L3 cache is shared among all of the cores in this quad-core processor here. Pretty good images of what goes on these things. These are tables that are in the book. Doesn't do a whole lot of good. It's third generation core, the processors, and the cache, what's available on the system. So hopefully you start getting the concept that as we start building the machine, the CPU is really important, the memory is really important, how fast it is, how much cache do you have can also become a big deal. What kind of cache? How much of each kind of cache do we have? Processor number, example, 2-core i7 processors identified as the i7 940 and the 920. So this is just the processor numbers and how each of these things are configured. The Centrino is a laptop performance. The processor, chipset, wireless network adapter are interconnected as a unit, which is going to make them work better, work faster, closer together. Anytime that they're closer together with the speeds that we're talking about, it's going to really affect the time that it takes to do any of these things. More tables. Selecting a processor needs to, and the tasks. Assemble a PC from parts. Not a big deal, really. Not as big a deal as it has been. It gets easier and easier and easier. Exchange a faulty processor. Again, I don't think that's such a big deal either. As long as you know what you're doing, you disconnect it, take the processor out, put the processor in. The key here is going to be getting it lined up, and pin 1 is going to be marked so that you know where it goes. Years ago, I was doing this class, and we took apart some functioning computers because we didn't have all the stuff laying around that we can just take apart and put it back together, not worry about because they don't really work. And somebody took apart a machine. Don't take anything out of it. Well, he couldn't resist. So they took the processor out. And then they put the processor back in wrong. So now all of a sudden, after you get done, restart the machine doesn't restart. What they've done is turned the processor 90 degrees. And it fit into the slot. They made that to where they not necessarily going to do that so much. But pin 1 is going to be marked on everything that you do. So you need to be sure that the pin 1 gets lined up. You may add a processor. If you add a processor, you're going to have a motherboard that supports that, a dual processor. Not a core, an actual physical processor. Upgrade the existing processor depends on what the motherboard is going to support, and that goes back to the motherboard documentation and what we can and can't do with that. How to match the processors to the system, install the processor on the motherboard. Installing the processor on the motherboard, not such a big deal. Matching it to the processor system, a little bit of knowledge is required there so that you know what you're actually reading on this thing and you buy a processor that does work. First requirement, processor that the motherboard is designated to support. That just seems to be the obvious, doesn't it? You'll get a list on the motherboard documentation. If you don't have the book, books are available on the internet, and I think that there's a link at the top of the middle page that goes to the different manufacturers on what you can do. Actually, many of them may be chipsets, but you can see what's available there. The best processor meeting the general system requirements for the user needs. What are we going to do? Gaming system, you want fast memory, fast CPU, fast video. What if you're in a corporate environment, you're going to do like Microsoft Word or Open Office and go on the internet? How much processing ability do you actually need for those things? And that's what you've got to determine. And that's what businesses want to know. What can we do? We want to do it really good. We want to look really good, but we don't want to spend a lot of money. So what do you actually need? And when you start going through these things, you've got to stop thinking about, this is what I would do at home. This is what I really want at home. but what would I do in business? What's going to support the business? May have to sacrifice performance for cost, and that may or may not happen. I'm a cheapskate when I go to buy a machine. So I'm not a gamer. What do I need to do? My wife does some processing. She has used things like QuickBooks, so I need the ability to do that. Spreadsheets, internet, email, Word, Excel, those kinds of things. So I don't need a high-powered system. I could get a high-powered system. It'd be really, start up really quick and then just sit there. But what do I need? What do you need in business? And those are the things that you're going to need. Installing a processor, a bunch of checklist points that are available, and this list is in the book, obviously. Guide and follow the directions, and the directions would, the things like install a processor before you put the motherboard in, whichever you want to do. A couple of important things here is use a ground bracelet, anesthetic gloves. What you don't want to do is create a short circuit between you and the processor, you and any of the components on the board. These have very thin walls, and even a static charge that you don't feel can damage the device, the solid-state device. And it's not necessarily going to fail at that instance. It may fail 2 weeks, 2 months, 2 years later because of the damage that you've done, because of you have made the wall thinner so that the electricity can jump across these things. Open the socket, pushing down on the socket lever, and gently push away from the socket. So what that's saying is you pull the lever out and then pull it up. Remove the socket protective cover that came with the machine. We're making the presumption here that we don't have a CPU in, so there is a protective cover on the thing. And basically, take it out, put it in. Don't force it in. The new ones are zero insertion force sockets, so that you actually ought to be able to drop it and it will go in. If you drop it and it doesn't go in, you need to be sure that you've got pin 1 lined up and that the pins are lined up on it. In the good old days, the bad old days, we used to have to actually put pressure on the pins to put the CPUs in, which also meant that you could bend the pins. That was a real issue. The zero insertion force and the LGA, the land grid arrays, where we have, instead of receptacles in the socket itself, we actually have little lands that stick up that connect to the CPU itself. One of the motherboards that we'll have today, we'll take apart. A couple of those are LGA, so you can see what goes on with these things. We can't tell if this guy's doing it right or not because we can't see if he's got an anti-static wristband. We would hope that for the book pictures that they would have done that. But you never really know with these things. And they're talking here, the gold triangle right here would mark the pin 1. And here they say a right angle. I've always say it's notched or cut off, angled off. The processor socket itself will have a mark that shows us that it has a pin 1 also. And those are the things that do need to be lined up. They've made some other things to make it, putting these things in wrong, more difficult. The manufacturers have all gotten a lot smarter as we go through the years. Ensure it's lined up, return the lever to its locked position so that the processor is now ready to use. General steps to install the cooler. These things are not all going to be the same, and sometimes they're a real trick to figure out how to get them in, how to get them out. Usually the instructions on getting them in is easy. They snap in, and then you say, oh, no, I need to take it out. Not always necessarily so easy. How are you going to unlock it, basically? The thermal compound is put a thin layer on this thing and maybe pre-applied. But if it's not, what it does is helps with the heat transfer to the cooler. So the thermal compound helps with the heat transfer so that we don't overheat these things. Locking pins are turned counterclockwise as far as they'll go. And push down And this is for a specific one. Push down on the locking pin and it pops in. Each of them, again, what you'll find out as you go through these and taking them apart, because I have you take them apart completely and draw them and then put them back together, is sometimes this takes as long as a lot of the other stuff. Most of the other stuff just pops in, pops out. The next thing is to set up the BIOS. The CPU is recognized properly. Each BIOS is going to be different. Last time we looked at a virtual machine BIOS, a very simple BIOS. Boot to these machines, and I think you can boot to these machines and look at them as a much more complex BIOS. So it's going to be a function of what goes on in the system. And this one detected this thing. The processor type is an Intel i7 CPU, 9200, 2.67 gig, Intel 64, EMT 64 capable 64-bit. Processor speed 2.66 gig, which matches up with a 2.67. The system memory speed 1076 megahertz. The data rate 4.8 GT per second. L1 cache 256K. L3 cache 8192. Total memory, and these are the slots. One of them is not installed, 2048, 2048, 2048, so we have 6 gig of memory in this thing as you go through it. But did it properly install things? And you notice that we talked about the cache memory. L1 cache is not very big. 256K is tiny. But it makes the system operate a lot more efficiently, even with that small amount of memory. And the reason is it's more expensive to put on the system. LGA, I'm not going to go through these steps again, verify that the system works. And again, put it in, and we still can't tell if he's got his stuff on or not. The right notch in this one, and I think the picture in the book probably shows it a little clearer. There is a notch right here, and then there's a mark down here, alignment up down here that aligns with that notch. Again, another attempt to keep us from putting the processor in wrong. So orient the processor is a big deal. You notice here we have these fins. These are all of this stuff in here for heat dissipation. Gives us a large surface area for the heat to go away from. More pictures, and this one more 4 alignment positions. How are we going to align this thing to be sure again that the processor is properly aligned? And I think this one has the little notch here, and would have something probably on the top of the CPU to say, hey, this is the pin 1. A lot of times you don't have anything here in this area. If we were going to, actually this would be the pin 1, wouldn't it? Sometimes these are chopped off and you don't have anything in here. You just need to be careful the way that you do the alignment of these things. Open the socket, more of the same. Processors are done. Notice we jump right from processors to memory. And this chapter is both of these things. When you look at memory, when you add memory on the new systems, you're going to just see the memory sockets. And in this one, we've got 2 black ones here and 2 blue ones here. They should be populated with the black to the black. First, you fill the black sockets, and then you fill the blue sockets. Then this one has got 1 populated black and then 1 unpopulated. So it only has 1 DIMM installed in the system. RAM holds the data instructions used by the CPU. SRAM, static RAM, and dynamic RAM, both are volatile memory. Volatile memory means that we turn the power off when the computer goes away. It's differentiated from USB stick, which you can take out and it keeps everything on it. So those things. The static RAM, the difference is static RAM costs more. It's going to be faster on the individual motherboard, and doesn't have to be refreshed as much as dynamic as DRAM. So DRAM has to be refreshed on a regular basis, like every clock cycle when we do it. Variations, DIMM, dual inline memory module, the large one. SODIMM or SODIMM used in laptops, it's a dual inline memory module, it's just much smaller. Micro DIMMs used in subnetwork. And RIM and SIM, RIM is RAM bus, which was a proprietary one, and they've got like a half a page through 2 paragraphs or a paragraph and a half in the book. It's not used anymore. They caused quite a stir and quite a problem when they first came out with the RAM bus because they were suing everybody and their brother for violating their patent rights. And some people they won with, some people just paid up, some went back to court, and I think that they lost. SIM, single inline memory module, going to be much, much smaller, and it is a very old system, and I think that you'll probably not ever see a SIM. You might see a RIM on an older system. RIM memory is also very expensive. All of this stuff, well, these things are very expensive now because they're old. It's kind of like trying to buy a part for an old car. If there's only one of them in the world, then somebody can charge whatever they want for it. Difference in these things, the data path, the width, and the speed, how the data moves from the system to the bus. And when we talk about the data path, we're talking about how big is the word size. If we'll go back to the 32-bit. In a 32-bit, we would have 32 ones and zeros going from the memory to the CPU, to the CPU module. In a 64-bit, we would have 64 ones and zeros, so we can send twice as much data in the 32-bit system. The bus speed is how many times a second that information gets sent to the CPU. These pictures are all in the book, or you can look on the internet to see what they look like. Each of them, you'll notice, has a notch in it, and they're all in a little bit different position so that you can't put the wrong kind of memory, theoretically anyway, or put it in backwards, put the wrong memory in the wrong memory slot, or install the memory backwards. Some of them look like they're in the middle. These kind of look like they're in the middle, but they are a little bit offset, so that you can't go there. The RAM bus RAM down here has these two really close ones. RAM bus RAM, you have to have something in every slot. It's kind of like the Christmas lights. When the one bulb goes out, they all go out. This is serial. It has a placeholder. You don't actually have to buy the memory. You can buy a placeholder which completes the circuit. The reason these are covered here, you're not going to find it in any new machines, but you may find it in some old machines. And if you don't have something in all the slots, it just won't work. This is some old SIMs. And you notice when I say old SIMs, how small these things are. 30-pin, 72-pin. As differentiated, go back to these. As differentiated from here, we have DDR3's 240-pin, 240-pin DDR2, 184-pin, 168-pin, and 184-pin for the RAM bus RAM. So the older systems, get going in the right direction here, 72 pins and 30-pin. 30-pin is going to be exceptionally old. 72-pin, when we got that, hey golly, we've really made things go much faster because the more pins, the more it can handle at any given time. Dual inline memory module, 64-bit data path. Independent pins on the opposite sides of the module. The older DIMMs are asynchronous with the system bus. Synchronous DRAM runs synchronously with the system bus. Asynchronous means that the speeds can be different. Synchronous means they run together at that speed. 2 notches, 168 pins as you do those things. DDR double data rate, SDRAM, 2 times faster than the SDRAM. It's just double the speed. That's why it's called double data rate. DDR2 SDRAM faster than the DDR, less power, DDR3, and then DDR4 is on the horizon. Each of them becomes faster more efficient. I think I have a discussion here in a little bit about adding an extra bit because we may or may not need a parity bit. The newer memory, we don't have parity memory anymore. When memory was not as good and you needed to actually ensure that what you sent was what got there, there was parity that worked with those things. Servers generally are going to have error correcting memory, which uses a parity. It can check to be sure what got there, and if there is a single error corrected, if there are multiple errors, it can only detect that there was an error. Number of channels they use, how much RAM is on one, speed, error checking, and buffering are all the things that are available. Early ones, memory was accessed one DIMM at a time, and then we go with dual channel memory. Controller communicates with two DIMMs at the same time, so if we can do two DIMMs at the same time, it's going to be much faster than doing three DIMMs, or two DIMMs, or one DIMM. Yeah. We also, the new ones have triple DIMM, or triple capability instead of dual access, dual channel, triple channel. And I think they've got some pictures of those here. Triple channels accesses three DIMMs at once. The triple channel, let's see if they've got a picture here. DDR2. Yeah, these things here. Let's see if we get that. Quad channeling introduced with the Intel Sandy Bridge. We have two DIMMs here and two DIMMs here. The reason that they put them on each side of the CPU, uses 8 memory slots, is it reduces the distance that it has to go. When we're going at these speeds, the farther away, the longer it's going to take it to get there. So in a quad, it can use 4 slots at a time. In the triple, let's see if they got the triple, yeah. In the triple, now this is the dual. Setting up a dual channeling, if you have the 2 slots, actually I got this backwards because I circled it here, but we'd have the 2 black or the 2 blue would set up dual channeling. If you have a single, if you put in the dual channel and then you put in a third DIMM, it would disable the dual channeling. So you have to have the memory slots filled with even numbers, basically, of DIMMs. In the triple channel, if you have the 3 configured, then you get triple channeling. There actually is another one back here, and you can see, I think here, that it's not snapped in. If you would fill up the 4th one, the triple channeling goes away. So you actually, by putting more memory in, have slowed the process now, because it can now only address the DIMMs one at a time instead of addressing the 3 of them simultaneously. Measured in megahertz or PC rating. DDR2 usually labeled PC2 and DDR3 labeled as PC3. In these things, single-sided DIMM are sold on one side. These are really brilliant, right? Single-sided on one side, dual-sided is on both sides. That can affect how fast it goes. The memory bank is the memory processor addresses the banks one at a time, and the banks 64 bits, are 64 bits wide. Dual rank sounds like it should be faster, right? But it's really not, because what they do, the DIMM provides 2 or more banks. It reduces the performance because first, to get the 64 bits, first it addresses bank 1, and then bank 2, and then bank 2, which is going to slow down the process, the ability of this thing to do this thing. Error correcting code, we talked about error correcting a little bit. What it does, it adds an extra byte, 8 bits, so that when you look at these things, instead of 64-bit, it's going to be a 72-bit DIMM. In the good old days, when we had 8 bits, we would actually, for the error correcting, or for the we would have an extra chip on the thing, so you'd have 9 bits, and the extra bit, or extra byte, actually, was to do that. The 9th bit here, odd parity, even parity, and odd parity. What this does when you say even and odd parity, and again, this is old systems, the parity bit's set to make an odd number of 1s or 0s, and then it checks to see when it got there. So if it has 1 error, it can tell you it has 1 error. But if it has 2 errors, it doesn't know, because if it's odd and you have an odd number of 1, so you leave it at 0. If I have 1 error, then it's going to become an even number of 1s. If I have 2 errors, it's still going to be an odd number. Buffered and registered DIMMs hold the data and amplify the signal. The registered DIMM uses registers. An unbuffered DIMM, there are no buffers or registers in this thing. Registered you may see with usually server RAM. Fully buffered DIMM uses the buffering techniques, and you can't mix buffered and unbuffered RAM. It just won't work. Latency, basically how fast it goes, row access strobe and column access strobe, CAS and RAS. When you look at these things, what we want to go to is the lower number. The lower the better. And it's going to be something like a CL something or another. So the lower is going to be better. Some memory modules are going to specify the latency, and this one's going to be a 5 in the technology itself. RAM bus, yes, expensive, slower, and gone. You may see it. If you have to replace the memory, it's going to be very expensive. And in some cases, with the price of computers that you use in a corporate environment, it might be cheaper to replace the computer than to buy the RAM bus. CRAM, continuity RAM. The continuity RAM is the placeholder module. Let's see if they got the picture here in just a second. Oh, I guess not. They have a picture. They have a picture of it in the book. It looks just like the one that we saw, except it doesn't have any memory module, any DIMMs, anything on it. Memory performance factors, the total RAM, the technology, the speed. We want to do this. The PC rating is related to the speed. What we do is take, if we had an 800, I'll do this because it's easy arithmetic, 800 megahertz bus and 8 bytes, multiply it by 8 bytes, then it would be PC 6400. See if I can get the 4 in there. So these things are going to, they're all related. Error correcting or non-error correcting, this the CL or the RL rating, and again the lower the better on these things. Single, dual, or triple or quad channeling. Remember, in the triple channeling, if you have 4 of them and you put the 4th one in, your channeling goes away, and it actually slows down the operation of the system. How to upgrade memory? That's a tough one, right? What's the first step in upgrading memory? What kind you got? Crucial, and since we're controlled, you guys can't do it here, but Crucial has a little app that you can run if you go there, and it will survey your computer, tell you what kind of memory, how much memory you have in it, how much you can add, and of course sell you a package to upgrade to the maximum. But what it is really handy for is to find out, if you're in doubt, what you actually need, so that you can go buy the correct memory for the system. So the basic technique, add more RAM modules that came, I bought it from Dell, and it came with 1 DIMM installed in the 4 slots that I had available. Problem solve, slower performance. The indicator that you need, Windows insufficient memory error messages. The system's going to run slow and the hard drive is beating itself to death. And the reason it's beating itself to death is paging information in and out of the hard drive. So if the hard drive starts beating itself silly, it's constantly running, you may want to look at adding RAM to the system. How much RAM do I need? You can ask all yourself, and you can look at the books, or there are a number of apps. Crucial is the one that I've used that says, hey, this is what you got, and this is the memory that you need, and this is how much you can put in, and here's our recommendation, and here, just add this to the cart, and we'll sell it to you. Windows 7 requires at least 2 gig, 32-bit, 4 gig. The RAM limit for the 32-bit is 4 gig. So if you need 6 gig or whatever else, you've got to go to a 64-bit system. This will show up as 30-something, and I've forgotten the exact number for the 4 gig in the 32-bit system. Somebody says, hey, I put 8 gig of RAM in my computer and only 4 gig showing, then a little bell ought to go off. You have a 32-bit system, 32-bit architecture, 32-bit operating system. Maybe I got a 64-bit architecture, but I installed a 32-bit operating system. That's all it's going to be able to handle also. Open the case, how many slots, how many are filled, the module imprint. The module imprint, where is the slot? What kind of memory can go into it? Physical size and the notch position. The motherboard documentation, and again, apps that are available to tell you what you have and what you need for these things. I read the motherboard documentation, and that's what we say lots on these things. Using DDR triple, what, dual channeling, what are we going to do? And remember, for the channeling, if you have an odd number of DIMMs in a dual channel, then you're going to disable the dual channeling. If you have an even number in the triple channel, that's not true. If you put 2 of them in, you'll have dual channel. Put all 3 of them in, you have triple channel. If you put the 4th one in, you disable it. I think some of this becomes repetitive here. Dual channeling allows 3 different DDR SIM speeds in one of the 4 sockets. If you do channeling, the channels have to match up with they have to be the exact same memory. The other 2 can be different, but these should be the same everything, including the same manufacturer, for the dual channeling to work properly. More things that you can read about. The RAM modules, where we want to erase it from our memory. Compromise if the exact match is not available. Registered memory. Mixing buffered and unbuffered. Mixing unbuffered with buffered makes it not work. Match the module and the manufacturer if possible when you do these things. The sites, the website, you to research your purchase, and it's going to have sometimes going to be listed in different ways. How do you install it? Again, the ground bracelet, turn the power off. And turn the power off on this, unplug the power cord. Be sure that the bus is drained. I think that you'll find in the new machines there's a little LED on the back that lights up, stays lit, and that means that there's power on the bus. You want to wait until that is completely gone before you start working on it. And that's where press the power button. The power button will drain down. Press the power button after you turn the power off and unplug the power cord. Press the power button. The power button will help get the power off that's held in the capacitors off of the bus. Handle memory modules with care. You shouldn't touch the metal contacts, so you want to hold them on edge when you put these things in. Don't touch the contacts. The contacts on all these things are generally going to be gold-plated. The oils from your hand will affect the connectivity of them by making them capacitive. It puts a little non-conductor in there. Don't stack them, look for the notches. We've had people that, in spite of all of that stuff, one time somebody had the ability to actually put it in backwards and short the memory, which is really tough to do with the new ones. Pull the supporting arms out, use the notches, put them in, and snap it in. They should snap in, and the little lock should actually come up and snap into place when you do those. Generally uncomplicated, not a big deal, but if you go to some of the commercial locations around and have them put them in, they charge like $50 to put memory into a system. The RIMs, it's going to be the same process, and what it really is, install the RIMs beginning with bank 0 followed by bank 1 all the way through. If the CRAM's already in the slot, remove the CRAM, but again, you have to have all the slots filled in RIMs, and hopefully you'll never see any of that. There was a big, when it first came out, there was a lot of controversy. Is it faster? Is it not faster? I don't know if the article's there. Tom's Hardware did a big research project on it and came up with some conclusions, which Rambus didn't necessarily agree with. Tom's Hardware, by the way, if you haven't been there to look at hardware, is a great place to go find out things. They do a pretty good job of keeping up to date. Processor, most important component to manufacturers, Intel and AMD, are rated at speed of the system, and it's going to have a multiplier of some kind that's going to run faster than the bus speed, so we'll have a multiplier. Multi-core, we have internal memory, cache. The cache is what makes it faster, and RAM. The more RAM in a Windows world, or actually in any world, the more RAM, the better. The caches, each of them are going to have their own L1 and L2 cache, and they're going to share the L3 cache in the cores, the number of cores in the processing unit itself. Processors have all core processors. Core of the processor, here, I'll get that right in a minute, has 2 arithmetic logic units, ALUs, and each core can process 2 threads at once, which means that as we go through these things, we're going to become faster and faster and faster as the architecture changes. The current ones, the Core, Atom, Celeron, and Pentium. The Atoms are kind of neat. They're not real high power going, really small little systems. And if you haven't looked, and I think you weren't here for one of the days, the system as you go out the door has one of these little motherboards on it. It's kind of neat just to look at, just to see what these things look like. It's not in a case that's just hanging on the back of the machine. It supports that whatever size monitor, touch screen that's out there on the back that has the scheduling and those sorts of things on it. The different families, and these things all change. The names change. The Phenom, Athlon, and Sempron processors. A processor that the motherboard supports, it's always handy. Otherwise, you've got an extra processor, and you can go buy a motherboard that will support your processor. Always follow the directions in the guide. And the DRAM is stored in 4 kinds of modules: DIMMs, which are the things that we use in CPU in desktops, SODIMMs, laptops, RIMs. Hopefully, you won't see in SIMs, which I seriously doubt that you'll see. SIMs are really, really old technology. Single-sided or double-sided can be DIMMs. Story about DIMMs, we one time got some double-sided DIMMs, and when we put them in, we got like half the memory because we go back to the motherboard up here where it says select something that it supports. Didn't support double-sided DIMMs. It only supported single-sided DIMMs. Those are all things that might happen to you. Dual, triple, or quad channels. This is all good because it addresses either 2, 3, or 4 DIMMs at the same time. And in the triple, we have 3. If we put in the 4th, then we go back to a single. DIMM's measured in megahertz PC rating. We looked at that, and basically the PC rating is the bus speed times 8 bytes, or 8 bits for the number of bytes. I'll give you the speed. Memory controller, we can have error checking, correcting memory, and that's typically going to be in a server where you really need it to be absolutely accurate. Buffers and registers are used to hold data and amplify the data so that it's close to the CPU, and when they write in a logical sequence, it can guess what's going to be next. RIMs require every slot be filled. Use the type, size, and speed that the motherboard supports. That makes sense that you use what it needs. So that takes care of processors and memory. Overview. Be sure to read the chapter. Questions. Just confused the heck out of you, right? Going once, going